All right, the purpose of this lecture is to reiterate what we've previously discussed on wave reflection and transmission, as well as look at a couple of examples and add some new material. So once again, this is the overview of Chapter 8 and some of the things that will be discussed in Chapter 8, and the goal for this lecture is to get through wave reflection and transmission at normal incidence. So we talked about before the fact that you have wave propagation in lossless media, wave propagation in lossy media, uh, and then what happens when the wave is incident upon a boundary of two different materials is you have what is called wave refraction as well as reflection, not shown in this picture. So the first thing to discuss is normal incidence, which is what we've discussed in class, and I'll discuss in review again here, where the normal incidence means that the direction of propagation of the wave is normal or perpendicular to the boundary. So the boundary here will come, basically it's coming in and out of the screen, it's perpendicular to the screen. When a wave is incident on a boundary with normal incidence, a portion of the wave is transmitted, a portion of the wave is reflected. We're going to call the impedance of medium 1 eta 1 and the impedance of medium 2 eta 2. Then these are just illustrations of oblique incidence, which we'll discuss in the next lecture. I'm not going to dwell too much on this other than to say if you missed class, we did talk about how the plane waves at boundaries is quite analogous to the boundary between transmission lines with different characteristic impedances, Z01 and Z02. So here's the model of normal incidence that we discussed in class. So we have an incident wave propagating in the positive Z direction, and we will just arbitrarily call the boundary between the two materials Z equals 0. And in this coordinate system, Z is pointing to the right, X is pointing up, and Y is pointing toward us, which then means if E is pointed in the positive X direction and H is pointing in the positive Y direction and the propagation is in the K direction. Now the transmitted wave will have the same vector directions for E, H, and K, but the reflected wave, because we're traveling now in the negative K direction, because of the relationship K cross E has got to equal H, the direction of the reflected H field has to shift in order to satisfy the boundary conditions. So each wave can be modeled. So we have the incident wave traveling in the minus Z direction. So this is the phasor form of the incident wave. The intensity or magnitude of the incident wave will be given a superscript I and a subscript 0. So this is just a constant. And it's pointing in the x hat direction. So in order to get the incident H, we take the cross product of the direction of propagation, Z hat, with the phasor vector E incident, and divide by eta 1, which then gives us an expression for H. The reflected wave, basically the electric field has now a superscript R for reflected. Also, it's in the x hat direction, but notice now that instead of minus jk1z, it's just jk1z because it's traveling in the negative direction. And so the same for H. Now the consequence of crossing a negative z hat with an electric field will get a negative y hat, causing H then to flip. Once again, the direction of propagation has the positive sign in the exponent. And finally, the transmitted wave. The difference there is we're in medium 2, so you notice we now have a K2. The E has a superscript of T for transmitted. In the cross product to obtain H, we're now dividing by eta 2, the impedance of material 2. And then the direction of propagation is in the positive direction, so it's a minus J. K is K2, and Z is still the direction of propagation. So we can get all of these expressions for incident, reflected, and transmitted waves. When we now look at the boundary conditions, the boundary condition at Z equals 0, E1 and E2 have to be 0 because both E1 and E2 are tangential, and the tangential components of E are continuous. Now in class we had a discussion saying the tangential component of H is continuous. From fields 1, the tangential component of B is the continuous field, but remember we're in a non-magnetic material, so mu1 and mu2 are equal. So basically that then means the tangential components of H are equal as well. We do that at the boundary at z equals 0, meaning all of these exponential terms are going to go to 1. And from that, we get that E incident plus E reflected has to equal E transmitted. We get that E incident over eta 1 minus E reflected over eta 1 has to equal E transmitted over eta 2. So combining these two equations and doing a little bit of algebra, you can get the reflected and the transmitted field in terms of the incident field. And from the coefficients that are functions of eta 1 and eta 2, we can express a reflection coefficient and a transmission coefficient respectively. So gamma, the reflection coefficient, is equal to the term in the parentheses in the first equation, and tau, the transmission coefficient, is equal to this term. So for normal incidence, that is the reflection and transmission coefficient. Once again, this is in a lossless media. Both medium 1 and medium 2 are lossless. They're both non-magnetic. So once again, here's normal incidence for reflection and transmission respectively. From this, the transmission is 1 plus gamma, and since we are in non-magnetic media, mu is the same for all of the eta expressions, drops out, and so we can actually put gamma in terms of the relative, and as well as epsilon naught being contained in every term. So we can now put gamma in terms of the relative values of epsilon. So once again, here's the expression for or the comparison between plane waves and transmission lines. In plane waves, we're dealing with a uniform plane wave. We're dealing with E and H fields, and we're dealing with impedances of space or impedances of media. The propagation constant is referred to, or the wave number is referred to as K1. In transmission lines, we were talking about currents, voltages, and impedances Z. But the reflection and transmission coefficients are exactly the same. K1 and K2 are the same as beta 1 and beta 2. Eta 1 and eta 2 are properties only of the material. In a transmission line, Z1 and Z2 are properties of the material as well as the geometry. So that's the primary difference in that. Power transfer, if you recall from chapter 7, the average power transfer is 1/2 of the real component of E crossed with H star. That's from the last section of chapter 7. So if we look in media 1, we basically, E has two terms, the incident part and the reflected part, and H has two terms as well, the incident part and the reflected part. We have to star the E here. We have to star the gamma in this expression. And so when you do that and you do the algebra, you find out that the average power is in the z hat direction. It's the incident wave's magnitude squared over 2 eta 1 times 1 minus the absolute value of gamma squared. Now if we look in medium 2, we can do the same exact calculation and get this expression, tau squared magnitude of E incident squared over 2 eta 2. Because we know that tau squared over eta 2 is equal to 1 minus gamma squared over eta 1, that tells us that the average power in medium 1 is the same as the average power in medium 2. The way this can happen, because clearly since part of the wave is reflected and part is transmitted, intuitively you would think that the incident wave would have higher power than the transmitted wave. But what happens is this reflected wave negates a portion of the transmitted power of the incident wave, because on the left-hand side in medium 1, you have a combination of a standing wave that's created by the reflected wave and the part of the incident wave that it's canceling out, and then you have a traveling wave that is basically what remains. So that's sort of the 1 minus gamma quantity squared as far as the power perspective goes. So that's the situation with power transfer. Okay, I want to look at this example, and then I'll stop the video and resume the video for a new example. Basically, this is a radome design. So in a radome, you basically have an antenna that's generating a beam. The beam comes through the dielectric, which is basically protecting the antenna, and then propagates onto a receiver. The radome shape is not planar, but because the beam is very narrow, we can approximate it as planar. We can also say it is a lossless dielectric in this example, called epsilon relative 9 and mu relative 1, so non-magnetic. And we'll choose its thickness to be D. And we're also told specifications that we require D to be greater than 2.3 centimeters. So that's roughly an inch. So, and the frequency of this radar is 10 gigahertz. So we can model this as an incident wave and a transmitted wave. And once again, from transmission lines, if medium 1 and medium 2 are the same, if the thickness of, medium 1 and medium 3 are the same, if the thickness of the radome is an integer multiple of the wavelength of the wave in the material, then no net reflection occurs. So I don't know if you covered that in your Fields 1 class on transmission lines, but basically as long as this is an integer multiple of the wavelength, then there's no net reflection. So at 10 gigahertz, we want to calculate what is the wavelength. So in air, we just take the speed of light divided by the frequency and get 3 centimeters. And then in the material, we take lambda naught and we divide by the square root of epsilon relative, which is 3. So basically it's 1 centimeter. So we can choose D to be 5 lambda 2 over 2. And in that case, the radome will be non-reflective as well as satisfying our criteria for being structurally stable.